Right, welcome back. MECH2320 motor controls. We're getting into chapter 36 here. We're going to talk about VFDs, or variable frequency drives. All right, we are going to do an extensive lab on VFDs. All right, we'll have a specific trainer that we're going to be going through. It's it's very specific to you being able to work up with a VFD and operate a VFD and make all that work. Another lab you're going to have where you're actually going to wire up a VFD and make it work as well. So a couple different opportunities here for you guys to actually understand what a variable frequency drive is and does, and kind of what the points of it, and the different methods of how we can control that frequency, and some things that might impact it. Okay, so when we talked about variable frequency control, all right, we talked about them with the consequent pole motors. We talked about changing the number of poles, right? Allowed us to change the to drop the voltage, which changed the frequency, right? So the other way is to actually put something on that changes the frequency. So when we talked about increasing or decreasing the number of poles, okay, that was more with the consequent pole motors. So we're going to get into actual VFD controls here, where we actually take a device that is a VFD, a variable frequency drive control, and put it in line with the motor, okay? And we want to be able to change the frequency of that, okay? So one method of this is called the alternator control, okay? So when alternators come in to control, this is slightly different than the alternator in your vehicle, okay? This is more for industrial applications and things like that. So what happens with an alternator is that the output voltage of the alternator is determined by the amount of DC excitation current that's applied to the rotor. So essentially, the output voltage must change with a change in frequency. Okay, so that's why there's a variable DC power supply that's put onto this. Okay, so the alternators that we use mainly work on conveyors where we have multiple motors. I'm going to step back a slide here. Multiple motors, all right, where we have to have them all change speeds at the same time so everything stays in unison, okay? So I already talked about, the output voltage. We put sensors on there to adjust, all right? It's going to tell what the speed is, and then it's going to adjust. Okay, so you can look at, the different type of motors there and how we would change the frequency now. So if we know that the motor has 2 poles, we could adjust the frequency from 60 hertz down to 10 hertz. Okay, so as we're adjusting the frequency, the lower the frequency, the lower the RPMs. Just like if we look at a motor that has 8 poles, all right, it's a 900 RPM motor when we're normally running at 60 hertz. If we dial that down to 10 hertz, it's running at 150 RPM. So there's how we're adjusting the speed, okay, to slow the motor down. So the motor can handle all these different speeds. So you just adjust it because you can adjust the frequency as you do this. Okay, a VFD drive, a variable frequency drive, it's a solid state drive. So remember, anytime we're talking solid state, and I've mentioned this multiple times, we're talking about transistors, okay, silicon, all those different things. What we breadboarded with in electrical class, or what we breadboarded with in digital electronics, those of you guys that took that, okay? Solid state control. It's really everything that we're talking about. Lots of use of different types of transistors, okay? So when we're looking at a variable frequency drive, the majority of them take an AC voltage and we turn it into DC, and then we change it back at the desired frequency. Now, it's not changed necessarily back into AC, it's changed into kind of like an alternating DC. Alright, and most of the motors can handle it. So just looking at the schematic here, if we take a look at the left hand side, alright, the little triangles with the slash in front, those are the SCRs we've talked about, alright, the silicon controlled rectifiers. Alright, the little transformer inductor looking piece, okay, that's the choke, so that kind of helps the flow through of what we're doing. And then what you see on the right hand side, there's 6 of them, alright, the T1, T2, T3 that's connected to that. Okay, those are BJT transistors, bipolar junction transistors. Okay, we didn't really cover transistors in the electrical class, but they're electrical switching devices. Okay, so the rectifiers, the SCRs, we're gathering the specific voltage that we want and rectifying it, and we're making it flatten out into DC. All right, we're choking it so that we can control it. We put a capacitor across it. We're really filtering it so that we fine in and we fine tune the that DC. Because remember, DC is either genuinely on or off, right? So we got to fine tune it to, if we're using 24 volts, we really want to flatten that out so that it's 24 volts. Okay, and then we use the transistors. Those are electronically controlled gates. You have a collector, a base, and emitter, right? And we can control those. So we can simulate AC with the DC by when we have the transistors open and close. Okay, electronic controls. So as those open and close, and we can set the timing for those and how they do that, that they're going to emulate essentially an AC signal, but it'll still be kind of a DC signal. Okay. And why do we use VFDs? Okay, we want to control drives up to 500 horsepower, and we want to be able to control the speed of those motors. All right, so we use the SCRs. Okay, remember those are silicon controlled rectifiers. That's how we're lowering the voltage, and the transistors are essentially, like I said, they're turning it on and off. They're simulating AC, but they're actually sending a square wave, not a digital signal, a square wave. So there's a difference, remember, between digital and discrete. Digital waves, all right, are always positive, on or off. Discrete waves can actually have negative polarity, just like you see here. So the square wave here that you see, that's a discrete signal. And we talked about those signals in the electrical class and what the difference is in how we use them. So this is kind of a sinusoidal type DC waveform, all right, that we can use to run the motor. And it doesn't have a big impact on motor. They actually handle the DC fairly well. Okay, so related problems with this, when we use the SCR power controls, okay, what happens is how those control the voltage. Remember, they chop that incoming waveform. Well, when they do that, we cause harmonics on the line. Okay, so other types of waveforms or other things that run interference. Okay, those can cause overheating of transformers, motors. It can cause fuses to blow and things like that. One major downfall is they actually can saturate the bipolar junction transistors. Now, when they are saturated, it doesn't mean that they don't work. Bipolar transistors can still work when they're saturated. So saturation means, all right, the collector base emitter voltage drops anywhere between 0.04 and 0.03 volts. It allows the transistor still works, but what will happen is we cannot have the speed of the switching then. It slows that down, which can destroy some things, okay? So, there's other methodologies that are in between there. You're switching, if we need to change the speed quickly, it will not happen as quick because of those BJTs that are in there, and they're operating at saturation. All right, so to help, with that saturation idiot, I don't really even know what that word is, but to help with that saturation problem, okay, or the saturation idea, all right, we use IGBTs, insulated gate bipolar transistors. So those have a much higher impedance, and they have the ability to turn on and off quickly. So they can still run in saturation, okay? We still allow them to run in saturation like the normally BJTs. However, they're actually still able to turn on and off quickly when they're not in saturation, or when they're in saturation. So where the other transistors, we couldn't have quick response, the insulated gate BJTs actually give us a much faster response time for that. So you can kind of see where they actually do pulse width modulation. Don't worry about that if you don't understand what that is. That's a whole electrical class where you go into signal analysis and things like that. Okay, but so what we're really doing is how we control the pulse width. Okay, that's the length of the square wave. So it's kind of like 2 periods, or how wide that wave is. Okay, so you can look at the pulse width. So on the left we have a common pulse width. It might be a millisecond. Okay, it's going to be a time value, and it usually shouldn't be nice and even, right? We want a nice balanced wave, but we can use those pulse widths, okay, of this discrete signal here to create that sinusoidal type signal that we send in. Okay, so advantages of the IGBTs. Okay, the insulated. The SCRs aren't used in the power supply. Okay, so that reduces the issue with the harmonics. Okay, the disadvantage though is the fast switching rate. Okay, the fast switching rate can actually cause voltage spikes to the motor. Okay, so next there's special motors that we can buy that work and are specifically designed to operate with VFDs. Okay, they're called inverted rated motors. So they have a separate blower on them so that you can continuously cool them. Notice there's vent fans on, so this is a picture of one, what it would look like as well. Okay, we have insulated paper between windings and stator core, so we're all trying to reduce the heat down here. Okay, and we add phase paper to terminal leads. If you don't know what that is, if you think about if you've cut open like cables or wire before, right, and there's like a paper type coating that's wrapped around like the ground wire or something like that. Same kind of concept there, okay? And then you have the magnetic wire. It has a higher rated insulation. So remember, magnetic copper wire, things like that, is actually coated. So that wire has a small coating on it. You know, when I've talked about you guys having to make Tesla coils or things like that, you use the magnetic copper wire that's insulated. It has a coat on it, okay? And then we have a large case. So these are all, to help out with any issues with VFDs. Okay, so using SCRs and GTOs. Okay, so we're going to talk a little bit about what a GTO is. It's a gate turn-off device. It's very similar to an SCR. Okay, but they use what we call thyristor or I cannot speak right now. They are called thyristors. Okay, so what a thyristor is it's a transistor, okay, but it can't be saturated. It's just a more powerful type of transistor where it is literally on or off. There's no saturation going on, so there's much more improvement there. We can control the switching, and we can have those two states of operation. That's really what we're looking for. So this is kind of how VFDs have developed over time. So with this one as well, instead of using the SCRs, all right, the silicon controlled rectifiers, we're going to strictly use diodes when we do this. So notice now we have some diodes, and then we have the GTOs that come into play. Okay, so this isn't that exact one. This one still has an SCR on it, but when we do this, okay, it makes a big difference. So when we do it that way, you'll avoid the harmonics on the line, any voltage spikes. You won't be able to have it when we actually use the GTO. Okay, so it's good to check it out. Make sure you read through the book. And like I said, we're gonna have a big lab where we actually work on VFDs and things like that. So if we take a look, so what's the point of using a VFD, a variable frequency control drive, right? Speed control. That's the biggest thing. We can dial down. We can change the frequency. Changing the frequency, slows the motor down. So remember, there's two methods of changing frequency, increasing the number of poles, where we have the consequent pole motors, or we use VFDs, where we change the frequency. All right, that also reduces the speed control. Okay, or changes so we can reduce speed if we need to. Okay. Very big advantage to this is we can do automatic speed regulation. Okay, so very important. So we have speed sensing devices on everything. So everything can be switched automatically at once, right? If we use the alternator, or just if we use the VFD and we want to regulate the speed, or right, you're on a conveyor and we put weight on that conveyor. Things are going to change. We want the speed to remain the same. So we want to be able to use a VFD so it can regulate the speed and automatically make the changes necessary so that everything works. Okay, so and then we have volts per hertz, which is how we're controlling this, and then we have a maximum and minimum hertz. Remember, hertz is frequency. That's the unit of frequency that we're controlling. So hopefully this helps give you a little bit of an idea how a VFD drive works. So we change that AC to DC. We grab the DC voltage at what we want, and then we output that DC voltage to the motor as we've already adjusted that voltage to adjust to the correct frequency. We control the frequency with that voltage with our switching on our transistors. So there's how we use the solid state device to get through all that. So as usual, guys, email me with any questions. Let me know if we need to team meet or Zoom meet. Else, I think you guys will enjoy this lab in class and being able to control the speed of the motor and things like that. Else, guys, have a great day. I'll see you in class.